Let's talk about linear approximation. In this section, we want to use the equation of a tangent line to approximate a function f of x at a point A in order to estimate the function values f of x near this point A. So if you look at this diagram we have right here, this L of x is the equation of the tangent line. So this is the equation of the tangent line. And this point A, f of A, this point right here, this is where our linear approximation occurs. So this tangent line really is going to be our linear approximation. So let's say, I know what the function value is at some point A over here, and I want to approximate the y value of the function at some point x near A. All right. So if I were to kind of go up like this, the actual function value is going to be whatever that y value is. So this right here, f of x, this is the actual function value. Now my approximation is going to be not the actual function value. What I'm going to do is I'm going to use the y value of the line. So if I were to project that onto the y-axis over here, this number right here, this is our approximation for f of x. So this blue y value is the approximate value of the actual value of the red one. Okay, so how am I going to write down my linear approximation? Well, the first thing we want to do is why don't we write down the equation of our tangent line? When I go to write the equation of my tangent line, the equation of my tangent line is going to be y equal to mx plus b, right? And in this particular case, I am going to use the fact that I am at the point A. So I'm going to highlight this. We're at this point x equal to A. Now, when I want to find the equation of a tangent line, I'm going to need two things. The first thing I'm going to need is I'm going to need a point. And for my point, that's just going to be a f of A, because I am trying to find the tangent to the curve at this point A f of A. The second thing that I'm going to need is I'm going to need a slope. And the slope of my tangent line is going to be given by f prime of A. We know that the meaning of a derivative is really the slope of the tangent line. All right. So now what I'm going to do is I'm going to use the point slope formula. And the point slope formula basically says y minus y naught is equal to m times x minus x naught. And in our case, that's going to mean that y minus f of A is going to be equal to f prime of A times x minus A. All right. So what I want to do is I want to solve for y. So when I solve for y, this is going to give me y is equal to f of A. I'm going to add f of A to both sides, plus f prime of A times x minus A. And this equation right here is really our linear approximation formula. Now, there's a lot of textbooks that they call the approximation L of x, L stands for like the linearization of this function, or linear approximation. Okay, maybe I should mention that. I'll write that up here. This is the linearization of f of x. Okay, so now we can write our linear approximation formula. Instead of calling it y, we call it L of x. That's just going to be f of a plus f prime of a times x minus a. So I'm going to highlight this because this is our big formula. And this formula is called the linear approximation of f at x equal to a. And as I had said earlier, we also call this the linearization of f of x. All right. So I want to make a point. My point is that usually a is chosen to be a point such that f of a is easy to calculate. Now let's look at an example of this in action so you'll understand what I mean by my comment up there. So in example 1, we're asked to find the linear approximation of the square root function f of x equal to the square root of x at x equal to 16 and use the approximation to estimate the square root of 16.1. So in this case, they gave us this point where we're supposed to calculate it at. In fact, I would say that we should really have written this as a equal to 16. And 16 is a good point to choose because 16 is really close to 16.1, and I happen to know what the square root of 16 is. So this is what I mean when I say usually a is chosen to be a point such that f of a is easy to calculate. So let's solve this problem. I'm going to need a few things. One thing I'm going to need is, I know that my f of x is equal to, let me write this in exponential form instead of radical form, x to the 1/2 power. I'm going to need to also know what f prime is. So f prime of x is going to be equal to 1/2 times x to the negative 1/2. In other words, I just used the power rule on x to the 1/2. So f of a is going to be really f of 16. That's going to be the square root of 16, which is equal to 4. And f prime of a is really f prime of 16, and that is going to be equal to 1/2 times 16 to the negative 1/2, right? And that's going to be equal to 1/2 times 1 over the square root of 16. Now the square root of 16 is 4. 1 over 4 times 1/2 is 1 over 8. Okay, great. So now I have all the pieces of my formula that I need in order to write down the linear approximation. So the linear approximation L of x is equal to f of a plus f prime of a times x minus a. That means that for us, this is going to be 4 plus 1 over 8 times x minus 16. Okay, this is my linear approximation. So let me highlight that. That's our linear approximation. We haven't quite answered the question yet, but we're almost there. So let's finish off this question. This question is really asking us, what is L of 16.1? So I just plug that in for x. I'm going to get 4 plus 1 over 8 times 16.1 minus 16. Now, we can simplify this a little bit. This is going to give us 4 plus 1 over 8 times 0.1. And if we plug all of this into our calculator, we get 4.0125. So this is our linear approximation for the square root of 16.1. So the square root of 16.1 is approximately equal to 4.0125. Okay? All right, folks, we'll look at more examples together in class. Take care.